Hi guys, I would like to start the next topic in physiology, the neural control and coordination. So we have various activities in the body, or particularly in any organism we have a number of activities, functional activities or physiological activities. These activities are coordinated by a number of systems, particularly two important systems in our body for synchronizing or integrating or coordinating the various activities. So what do you mean by coordination? So we have different organs in the body, and these organs are interacting with one another, and so that they can complement the functions of each one. So the functions of each one being complemented because of the integration or because of the synchronization, because of the coordination between the different organs. As I mentioned earlier, we have two coordinating systems. One, the nervous coordination, another one, the chemical coordination. The nervous coordination is brought out by the nerves, and the chemical coordination is brought out by the endocrine system. And these two systems normally jointly coordinate and integrate the various activities of the organs so that the different organs in the body they can work in a synchronized manner. So synchronization is the effect of the chemical coordination as well as the nervous coordination. Now in this chapter we would like to go through the first one, what we have regarding the neural coordination. So what do you mean by actually neural coordination? So we have the nervous system in the body. The nervous system consists of a number of actually the components. The components are responsible for making the coordinating system. So the neural system provides, that an organized network of point-to-point coordination or point-to-point connections. Suppose you are touching an object, you can feel the sense immediately. This is because of point-to-point connections. So that there is a coordination which takes place in the fastest way, in a high velocity way. But in the case of endocrine system, which provides chemical coordination, not actually very quickly, the integration happens to occur mainly through the chemicals, namely the hormones. Anyway, if you are comparing the two systems, which one of these two is the fastest one? The nervous coordination, because it is having a connection, point-to-point connection. That is why the impulses are being conducted very quickly from the central nervous system or from the organs to the nervous system. Whereas in the case of chemical coordination or the endocrine system, it releases hormones. Through these hormones only just we can have, that is normally the various activities being brought about, but not in a fast way but in a slow manner. Now let's take about the neural system or the nervous system, the various components. If you take any animal, the neural system is made up of nervous tissue. The nervous tissue in its turn is being formed of actually organized network of nerve cells, what are called the neurons. So the neurons are the structural and functional units of the neural system. So it is a part or the component of the neural tissue. Suppose you are taking the neural tissue, it is being formed of these nerve cells along with non-nervous cells, what we can call as neuroglia. We'll see later about. So the neural system of all animals is made up of simply a nervous tissue, and that one is being formed of an organized network of what is called the nerve cells or the neurons. And what is the role of that neuron? I mentioned earlier, it is a structural and functional unit of the nervous system. It is normally responsible for detecting the stimuli, receiving the stimuli and transmitting the stimuli and conveying the same to the central nervous system. Transmission or conveyor. So it's conveyance. So the neurons can detect, receive and transmit different kinds of stimuli and conveying the same to the central nervous system. So the nervous system is actually specialized what for? For conducting the information. How for the information being conducted? So it is the nervous system responsible for conducting the information, but the information is conducted in the form of electrical impulses from one part of the body to another. So the way of conduction of impulses by the nervous system is in the form of electrical impulses, and these impulses are conducted from one part of the body to another. So the structural and functional units of the nervous system is the nerve cell, which is concerned with what is called the detecting, transmitting and also just receiving the stimuli and conveying the same one to the central nervous system. And all these impulses be conducted only in the form of electrical impulses. So what about the nature of the nervous system or the neural system in the case of different animal groups? If you are taking the simple animal group, for example Hydra, it is composed of only an organized network of nerve cells. The nerve cells are non-polarized in the case of Hydra. Simply there is a nerve network is formed, but there is no specific brain or any other structures formed in the case of Hydra. The cells are found scattered on the surface of the body, triangular in shape, non-polarized, and they conduct impulses in any direction. But the neural system is well organized, but in the case of, for example, some advanced invertebrates like insects, there they have brain and different types of ganglia. But there is no organized brain. Somehow we can call the so-called brain formed of ganglia and different types of ganglia and also the nervous tissue. There is a composition of the nervous system in the case of insects, somehow advanced when compared to Hydra, having brain, different kinds of ganglia, and also we have the nervous tissue. But in the case of vertebrates, the nervous system is well developed. We have well organized and well developed nervous system in the case of vertebrates, including human beings. So, how are the informations actually received or perceived by the body? So, we have different types of stimuli. Some of the stimuli are coming from what is called the external sources and some others from the internal sources. For example, hungry, feeling thirst. These are all what we can have, the internal stimuli. External stimuli, for example, the electrical stimulus or the mechanical stimulus or chemical stimulus or light stimulus or the sound stimulus. They are coming from outer source. They are called external stimuli. So, information relating to the external and internal environment are normally perceived or received by certain specialized sensory organs or the receptors. For example, you have the nose or the ear, the internal ear concerned with the sound perception, or the tongue. So these are all the different kinds of what we can have, the sensory structures or receptor organs concerned with the perception of information normally from both external and internal environment. And these organs have certain specialized cells. And these cells are responsible mainly for transmitting the stimuli, those stimuli falling on them. It may be mechanical or electrical or chemical. Any types of stimuli falling on these cells have been normally transformed into electrical impulses and conveyed to the brain where the interpretation of the impulses is taking place. So, the receptors are concerned for perceiving the stimuli, then just transforming the stimuli into what is called electrical impulses, and these impulses being conveyed to what is called the brain, the central nervous system, where the interpretation occurs. That results in what we have just the response. Now the human neural system. So if you are taking actually any nervous system or even the case of human body, we have two major nervous systems. One is called the central nervous system, another one the peripheral nervous system. The flow chart shows. The central nervous system normally localized in the mid-central axis of the body consisting of brain and spinal cord. And the peripheral nervous system includes those nerves originating from the brain, spinal cord, etc. So these are all the nerves originating from the brain and spinal cord, and they together constitute the peripheral nervous system. So if you are taking the peripheral nervous system, once again we have somatic neural system and then what is called autonomic nervous system. The somatic neural system normally includes the nerves, mainly the afferent nerves and efferent nerves, and those which are normally conveying the messages towards the central nervous system and also conveying the messages from the central nervous system towards the peripheral organs. They are concerned with actually the soma of the body, namely the somatic neural system, mainly connected to the muscles. Afferent nerves and efferent nerves, these are all the actually normally nerves connected to the muscles, the skeletal muscles. And whereas the autonomic neural system, it is an independent nervous system. It is working in an antagonistic way because it is being formed of two components. One is called the sympathetic nervous system, another one parasympathetic nervous system. Both together constitute what is called the autonomic nervous system, independent nervous system. And this nervous system is actually working independently, independent of the central nervous system. And they are again converted, actually divided into sympathetic and parasympathetic. These two are working in an antagonistic way and just bringing about the coordination of particularly just the visible muscles or the smooth muscles and also the involuntary organs like the glands. So both the sympathetic nervous system and parasympathetic nervous system regulate the functions of involuntary muscles or the involuntary organs and also the glands, etc. or the smooth muscles. Now the central nervous system. So you know that one, the commanding position. So it is actually the central nervous system. Normally we can say the brain is the commanding center and controlling the various activities. Anyway, together with the spinal cord, it is considered as a site of information processing and control. receiving the information, processing the information, and then just controlling the activities of the various body. So normally the central nervous system includes, that one, brain and spinal cord, and that one is responsible for coordinating the various activities of the body. That is why this site is called as a processing site and also the controlling site. The command is given mainly by the brain. Now the peripheral nervous system, those nerves what I mentioned arising from the brain and spinal cord and associated with these two structures together constitute the peripheral nervous system. If we are taking the peripheral nervous system, we need two ways. One from the organ to the central nervous system, another one from the central nervous system to the organs. And for that we need two different groups of nerves. One group of nerves may be the afferent fibers, another one what is called the efferent fibers, the one which is moving, the one which is moving away, the one which is moving towards. So the afferent fibers are those nerve fibers, normally they are carrying the impulses from the various organs and tissues of the body towards the central nervous system. So here is given the illustration, the tissues and organs to the central nervous system actually carried by the afferent fibers. Also they are called sensory fibers, another name for that one. Those nerve fibers originating from the tissues or organs and conveying the message to the central nervous system. And the second one, the efferent fibers, these fibers transmit normally the regulatory responses or the motor responses. That is from the central nervous system to the just actually concerned peripheral tissues or organs. So moving away from the central nervous system, carrying the messages towards the peripheral tissues or organs, they together constitute what are called the efferent nerves. So here is the equation, you see that one central nervous system towards the tissues or organs, that is via efferent fibers. So efferent fibers moving towards the central nervous system and efferent fibers normally moving away from the central nervous system. Now what are the divisions of the peripheral nervous system? I mentioned just in the flow chart we have seen the central nervous system includes brain and spinal cord and also including the various types of nerves, the somatic nerves, and we have generally speaking, and now just we have the peripheral nervous system includes the somatic nervous system and visceral nervous system or what is called autonomic nervous system. So what do you mean by somatic nervous system? Generally speaking, two different types of nerves under the central nervous system. I mentioned afferent and efferent, that is intended on use. Now that also coming into the peripheral nervous system only because they are all leaving from the central nervous system and also moving towards actually the central nervous system. They together also coming under the category of peripheral nervous system. Now another divisions of peripheral nervous system, we have one, the somatic nervous system. You see that one, it relays impulses from the central nervous system to the peripheral organs, particularly the skeletal muscles. Generally speaking, peripheral organs, but we can say peculiarly, specifically, the somatic nerves always carry impulses from the central nervous system to the skeletal muscles. That's why they are called as the somatic nerves and the system is called somatic nervous system. Whereas the autonomic nervous system normally transmits or relays impulses just from the central nervous system to the involuntary organs and also the visceral muscles or smooth muscles. That's why they are called as simply autonomic nervous system. So they have the nerve fibers that carry the information, the motor information, the regulatory messages from the central nervous system to those organs which are not working under the control of the brain and spinal cord. They are called as involuntary organs and also the smooth muscles of the body. So these systems, these nerve fibers together constitute autonomic nervous system. And which one I mentioned, we have sympathetic and parasympathetic. They are working in an antagonistic way, we will see later. So what are the divisions of the peripheral nervous system? The somatic neural system and autonomic neural system. Under the somatic neural system only we have received, for example, the somatic nerves or the afferent and efferent nerves we have. And autonomic nervous system we have the sympathetic and parasympathetic nerves. They carry the impulses to and away from the central nervous system, but connected to the smooth muscles as well as what we call the involuntary organs. Those organs which are not working under the control of the brain and spinal cord are controlled by this autonomic nervous system. Now autonomic nervous system, I mentioned already. So it is an independent system not working under the control of the brain. It is further classified into sympathetic nervous system, parasympathetic nervous system and also visceral nervous system. To some extent the third category. Mainly we have sympathetic neural system or nervous system, parasympathetic neural system or nervous system along with together a small, just a bit to be added to this one, visceral nervous system. Now nervous tissue. So what do you mean by actually nervous tissue? See, the nervous tissue is the one which makes up, that is what is called the nervous system. It is the main constituent of the nervous system, the component of the nervous system. So if you are taking actually the component of the nervous system, the nervous tissue, it is being formed the functional unit, namely the nerve cells or the neurons, and a connective tissue other than the nerve cells, what is called the neuroglia, which forms more than actually half of the volume of the neural tissue. So our brain is formed of actually billion nerve cells, but that one, if you're all accumulated together, they form only small mass, but we have the volume of, that one 1500 cubic centimeter. This is because of the large volume of the connective tissue, namely the neuroglia, the supporting tissue. So the nervous tissue is formed of mainly the functional unit, namely the nerve cells or neurons, and also the supporting tissue, the binding tissue, connective tissue, namely neuroglia. Now let's see something about the neurons, the functional structural units. So if you are taking for example the cells in the body, all the cells have the ability of dividing. 1 into 2, 2 into 4, 4 into 8, like that we have a number of cells. But in the case of certain cells, say an example of muscle cells and also the nerve cells, they do not increase in number. Whatever number we had at times of birth, we had the same number of cells now also. This is because of the inability of these cells to divide. The nerve cells and muscle cells never divide, and only certain extent the connective tissues divide, but not these nerve cells and the muscle cells. What is the reason for the nerve cells which do not divide? Let's see that one. So the fully developed neurons of the nerve cells are very highly specialized cells for the conduction of the impulses. But they do not have the centriole, the one which is taking part in the cell division. So that is why these cells do not have the ability of dividing because of the absence of the centriole. No centriole being present. So that is about a simple definition. Actually the neurons are functional structural units which do not divide because of the absence of centriole. Now we can have different types of actually neuron based on functions or based on just some other categories. Now let's take the first one based on the functional aspects. Based on the functions, we can have two different types of nerve cells, or two different types of nerves, or two different types of neurons. Sensory neurons or afferent neurons. They combine together to form the afferent nerve fiber or afferent nerve. Motor neurons or efferent neurons. So what do you mean by sensory neurons? Those neurons which conduct impulses from the receptors, for example, the skin or eye or nose or tongue, or even from the ear, and these cells, the nerve cells, are called the sensory neurons. Those nerve cells which conduct impulses from the receptors towards the central nervous system. And we have also another one, that is motor neurons. We have motor neurons. And these motor neurons are actually also called as efferent neurons. And these neurons are responsible for conducting the impulses from what is called from the central nervous system towards what is called the peripheral organs. So we have two different types of neurons based on function. One is sensory, another one motor. This is the second type. It's missing, it will be replaced soon. Motor, also called as efferent. Motor neurons also called as efferent. So the motor or efferent neurons conduct impulses from the central nervous system, that is from the brain and spinal cord, towards the effector organs. So sensory neurons conduct impulses from the receptors to the central nervous system, and the motor neurons, or just actually the efferent neurons, conduct impulses from, that is what is called from the brain or from the central nervous system towards the effector. So receptor to CNS, that is what is called sensory. Then CNS to what is called effector, that is a motor. Now another category, another classification of the neurons based on the presence of number of axon and dendrites. Based on the number of actually axon and dendrites. Accordingly, we have three different types of neurons. And just actually I mentioned already, based on the function, just based on the functions, we have motor or efferent neurons conducts impulses from the central nervous system to the effectors. And also we have some association or interneurons in the central nervous system or in the spinal cord. So these are all connecting the sensory and motor neurons. They are connecting the sensory and motor neurons. So there is about one category based on the functions. Based on the functions. Now the second one based on, that is number of axons and dendrons. Based on the number of axons and dendrons present or dendrites present in a nerve cell, we can have again three different types. Based on the functions, three types, and now based on the functions, we have three types. One, unipolar neurons. The second one, bipolar neurons. The third one, multipolar neurons. Out of the three, the one which is uncommon is unipolar neurons. The one which is uncommon is unipolar neurons. So this unipolar neuron has only one, just actual axon, no dendrites. That is why it is called as unipolar. And this type of neuron is normally found in the case of photoreceptor cells, namely the rods and cones of retina, and normally found in developing cells or in developing embryos or in the embryonic stage, because that is a stage of formation of nerve cells in the various organ systems. That is why this is common in the case of actually organisms during their developmental stage in the embryonic condition, and also found in the case of rods and cones, namely the photoreceptor cells in the retina, having only one axon and one cell body. Then the second one, bipolar neurons. Neurons having one axon, one dendron. Neurons having one axon, one dendron. Now this is the axon and this one being the dendron or dendrite. So neurons having one axon and one dendron are said to be what is called simply, that is bipolar neurons. They are found in one of the layers of the retina. If you are taking the retinal layer, we have pigmented layer, rods and cones layer, and bipolar layer, ganglionic layer. Like that, we have many layers are found in a retinal layer. That is what is called the photosensitive layer. And one of the layers is called bipolar layer, where you have this bipolar neurons. So bipolar neurons are found only in the retina, not found anywhere else in the body. Remember that one. Then multipolar neuron, it's the most common type of neuron. The well-developed nerve cells are mostly multipolar in nature. The meaning for that one, they have normally many dendrons and only one axon. So a cell with one axon, unipolar. A cell with one axon, one dendron, that is what is called bipolar. A cell with what is called many dendrons and one just axon, that is said to be what is called multipolar neurons. And this multipolar neurons is a well-developed one, found mostly, that is actually the developed organisms or in the adult condition. It's the most common type. And mostly found, if you want to say specifically, it is found in the cerebral cortex region. It is found in the cerebral cortex and also other parts of the body, but specifically speaking, we can have in the cerebral cortex. Now we can have the picture. Now the fully developed neurons. Now the fully developed neurons are very highly specialized cells, just what is seen already, the same one being repeated once again. Now let's see the structure of myelinated multipolar neuron. Structure of myelinated multipolar neuron. Now a microscopic structure is actually showing a cell body. A neuron consists of a cell body, a number of dendrons or dendrites, and then one axon. This is the simplest structure. Cell body, axon and dendrites. The cell body is also called a cyton or soma, centron or pericardium. The cell body has different names: cyton, soma, centron, pericardium. So I mentioned earlier, this cyton has many dendrites, which are normally carrying impulses towards the cyton. They are carrying impulses towards the cyton. And one axon. That axon actually carrying impulses away from what is called the pericardium. So we have many dendrites which conduct impulses towards the cyton, and only one axon which actually carries away the impulses from the centron to actually another axon. This is happening normally in the case of this one. Many dendrites which normally conduct impulses towards the cyton, one axon which carries impulses away from the cyton. Now we have just a cyton and then one axon. Now the part of actually the soma, now this is the cyton or soma, the part of the soma from which what is called the axon arises. This part is called axon hillock. This is the axon hillock. The part of the body of soma or pericardium or cyton or centron where you have actually the axon arises is called as axon hillock. Sometimes, normally in some cases, we have this axon produces some lateral branches like this. These lateral branches of the axons are called collateral axons. It's a rare instance. The axons may produce some lateral branches and these branches are together called as collateral axons. It's a rare instance. Now what about the cytone? The perikaryon or the cytone or the cell body or centron has a centrally located nucleus like this. This is the nucleus. The nucleus is surrounded by some darkly staining granules. The darkly staining granules just present around the nucleus are called the Nissl bodies. These are all the Nissl bodies. These Nissl bodies are rich in ribosomes and that is why they are involved in the process of protein synthesis. The Nissl bodies found in the cytoplasm around the nucleus. They are darkly stained bodies rich in ribosomes and they are involved in protein synthesis. That is what is happening. The main function of the Nissl bodies are protein synthesis. Then axon. So normally we have just actually the name of the plasma membrane has been given differently. In the case of muscle cell, it is called what is known as sarcolemma. Likewise, the plasma membrane of the axon is called as axolemma, and the protoplasm of the cytoplasm enclosed by it is called axoplasm. The membrane of axon is called axolemma, and the cytoplasm of the axon is called axoplasm. Normally, the axon is surrounded by a series of fatty insulating layers, a series of actually closely placed. Suppose this axon, we have a number of closely placed insulating fatty layers. Now this is the axon center. We can see later about if you make a section of it, the axon being surrounded by a closely placed, a series of closely placed insulating fatty sheets, and they together call us what is known as myelin sheath or Schwann sheets. The axon is surrounded by a closely placed insulating fatty sheets and they are together called as myelin sheath or the Schwann sheath. We'll see more about later. Now the axon is a long actually fiber which may be branched at its terminal end. Each branch at its end has a bulb-like structure. That bulb-like structure is called synaptic knob. Suppose this is the axon. If you are taking any axon, I am mentioning this is the branch and each branch ends in a bulb-like structure. This is the axon and here we have the cytone. Now this is actually the end of the axon branch which is bulb-like and that one is called synaptic knob, which contains a number of what is called vesicles called synaptic vesicles. These synaptic vesicles are filled with what are called some chemicals, namely the neurotransmitters. They are responsible for the transmission of impulses across the synapse. We'll see later about the conduction of impulses, the mechanism. So anyway, normally each axon ends in actually it's a branch and each branch ends in a bulb-like structure and each bulb is called synaptic vesicle or synaptic knob, which contains a large number of vesicles called synaptic vesicles filled with fluid and neurotransmitter. Maybe it is acetylcholine or dopamine, serotonin or sympathin, etc. according to the nature of the nerve fiber. Generally the vesicles are filled with what are called just the neurotransmitters responsible for chemical transmission at the synapse. So I mentioned earlier the axons normally transmit impulses away from the cytone, away from the cell body, away from the soma or away from the pericardium, and just actually transmitting the impulses either towards the synapse, the junction between the two neurons, or towards a neuromuscular junction, the junction between the nerve fiber and the muscle. That is called neuromuscular junction. So anyway, the axons transmit impulses away from the cytone and the impulses are moving either towards the synapse or towards the neuromuscular junction. Now there are two different types of axons. This is based on the presence or absence of the fatty layer, namely the myelin sheath or medullary sheath. So accordingly we have one myelinated axons, another one non-myelinated axons. That one with myelin sheath, another one without myelin sheath. So the myelinated nerve fibers are actually enveloped with what are called the Schwann sheaths or Schwann cells. So normally a single cell which forms series of layers around the axon forming what is called the myelin sheath or the Schwann sheath. So the myelinated nerve fibers are ensheathed by or enveloped with Schwann sheaths or Schwann cells. and this one form what is called a myelin sheath around the axon. Only a single cell forming a sheath around it. So it may be called a Schwann sheath, or simply we can say Schwann cells. And such sheath is being absent in the case of non-myelinated nerve fibers. Now let us compare the differences between the multipolar neurons of the two types named the myelinated neurons and unmyelinated neurons. If you compare that one, the name itself implies that one, those with myelin sheath and those without myelin sheath. And here if you are taking the nerve cell at regular intervals, suppose we are having the axon like this, and now if you are taking the myelin sheath, this is the medullary sheath, it is broken at regular intervals. This is the point where it is being constricted and it is being broken. That is what is called the point of constriction. So there is a point of constriction, what is called nose of Ranvier, being found in the case of myelinated neurons. Now what I represent is a part of the axon enveloped by the fat layer. This is the fat layer and this is the axon. And now this fat layer is normally broken at regular intervals or being constricted at short intervals, and that one is called node of Ranvier. So this one, nodes of Ranvier, and that being present in the case of only in the case of myelinated fibers and being absent in the case of that is unmyelinated or non-myelinated neurons. Now there is a point of contact, what we can say, that is synapse. We'll see later about that one. At that point, at the point of contact or synapse, you know that when the impulses are conducted in the form of what is called chemical impulses, not by means of electrical impulses. The impulses are conducted at the point of synapse by chemical means, that is being brought about by neurotransmitters. We have different types of neurotransmitters. One such neurotransmitter operating at the synaptic, that is cleft or at the synapse of the myelinated neurons, is called acetylcholine. So acetylcholine is a neurotransmitter at the synapse in the case of myelinated neurons. That is why these neurons are called cholinergic neurons. This is because of the nature of the release of the neurotransmitter. So the neurotransmitter substance is what is called just acetylcholine, and that is why it's called as cholinergic neurons. Whereas in the case of unmyelinated neurons, the neurotransmitter is in the form of sympathin, which is similar to adrenaline hormone. Hence, these neurons are called adrenergic neurons. This is based on the nature of the release of neurotransmitter. Cholinergic, where you have acetylcholine, particularly at the end of myelinated neurons. But in the case of unmyelinated neurons, particularly specifically found in the case of sympathetic and parasympathetic nervous system, the chemical transmitter, the neurotransmitter, is in the form of adrenaline or just a sympathin, that's with adrenergic neurons. Now, actually, the acetylcholine released in the neural cleft or neural synapse is destroyed once their function is over by means of an enzyme. So, the active moving of acetylcholine is brought about by what is called acetylcholine esterase, the one responsible for destroying the acetylcholine as soon as its function is over. Whereas in the case of just a sympathetic nervous system or unmyelinated neurons, the sympathin release at the synapse being destroyed by MAO, what is called monoamine oxidase. So here it is actually acetylcholine esterase, and there it is called monoamine oxidase. Then, where are they formed? The myelinated neurons are normally in the white matter of the central nervous system. And also, just actually central nervous system means which includes both brain and spinal cord, but here I represented white matter of central nervous system and spinal cord, and also in the cranial nerves. So myelinated neurons are found actually in the white matter of central nervous system and spinal cord and cranial nerves, whereas the unmyelinated neurons are found in the gray matter of the central nervous system and also in the autonomous nervous system and also in the somatic neural system. So they are found in the nerves, the somatic neural system, what we have afferent and efferent nerves. An autonomous nervous system includes both sympathetic and parasympathetic nerves. There you have the grey matter along with what is called just actually the grey matter of central nervous system, where you have this what is called unmyelinated or non-myelinated neurons. Now the mode of conduction of impulses in the myelinated neurons is called saltatory. This is because of the presence of actually nodes of Ranvier. That is why the impulses are conducted at a faster rate, 50 times faster than that of the impulses conducted by non-myelinated neurons. So, the speed of conduction of impulses is always higher in the case of myelinated neurons. This is very fast, and that is what method we have saltatory conduction because of the presence of nodes of Ranvier. But here in the case of actually unmyelinated neurons, no such nodes of Ranvier, so the impulses being conducted in a streaming way, and the speed is also very slow. So these are all some of the differences between actually the multipolar, myelinated and the unmyelinated neurons. Now, about what is called the Schwann cell. So we have, in the case of myelinated neuron, we have an outer fatty layer formed by Schwann cell. And each Schwann cell is nothing but a single cell having the membrane, its plasma membrane. The plasma membrane of it actually wraps itself just like a roll-up carpet like this. This is a single cell. This is what we have, the Schwann cell membrane wraps itself around actually just like a roll-up carpet, just like a roll-up carpet. Now this is like a roll-up carpet, round and round the axon. Now this is the axon. A single cell having the membrane being formed in many series, just like a roll-up carpet, round and round what is called the axon. Not many cells, only one cell. So if you are taking the structure, we'll see now. I'll tell you the diagram. So this is what we have with reference to the myelinated multipolar neurons, what represent the structure. Now in the nervous system we have the largest nerve cell, what we call this one, the Purkinje nerve fibers or the Purkinje neurons. Now this is what is called the section through a myelin sheath. Now if you are making a section through the axon, now this is the axon. This part what I showed is nothing but the axon, which is being surrounded by what is called the Schwann cell. The Schwann cell is actually wraps itself just like what is called a roll-up carpet round around the axon. You see that one, only the outermost layer contains a cytoplasm. Now this is a Schwann cell. So now this is a Schwann cell, a single cell. Only its outer, actually the membrane contains a cytoplasm. Now this is a cytoplasm and this one being the nucleus. This outermost layer containing nucleus and cytoplasm of the Schwann cell is called neurolemma. See, this is axon and that one is the nucleus of the Schwann cell, the second one. And we have the all together called the Schwann cell. And now these many layers together constitute the fatty sheath or the myelin sheath. Only the outermost, actually the membrane encloses a cytoplasm with the nucleus and that is called neurolemma. So the Schwann cell is actually forming the neurolemma as well as what is called the fatty layer. Don't forget that one. The fatty layer is being repeatedly produced by series of the membranes of the Schwann cell. The outermost membrane of the Schwann cell which encloses a cytoplasm with the nucleus is called the neurolemma. This is what we have. Just what I mentioned just there in the notes also. See that one? So only the outermost layer of the membrane encloses cytoplasm and the nucleus and this layer is called a neurolemma. Now we have narrow constrictions of just about 1 millimeter length are present between the series of membranes. And these constrictions are called as nodes of Ranvier. We have some constrictions formed about 1 millimeter length just between what is called the successive membranes or the successive layers. And these constrictions together constitute the nodes of Ranvier. We can see these nodes of Ranvier only in the case of that is the myelinated neurons, not in the case of unmyelinated or non-myelinated neurons. Once again repeat, here this is the axon, the one, number one indicating, and then these are all the layers, repeated layers, just like a roll-up carpet, and that one enclosing the axon, and that is forming the medullary layer. This is the outermost membrane enclosing the nucleus and cytoplasm, forming the neurolemma. The whole cell is called the Schwann cell or the Schwann sheath. And now just we have the fifth one. This one is a neurolemma, the outermost membrane enclosing the cytoplasm, and the nucleus is called neurolemma. So anyway, the fatty layer and neurolemma together produced by the Schwann cell or together called as a Schwann sheath. Now what is neuroglia? So the neuroglial cells normally a part of the nervous system, what I mentioned, actually other than the nerve cells, and their main function is just to support and protect the neurons. They are found along with the nerve cells. Their main function is to support and protect the neurons. And I mentioned earlier, even to begin, when I talked about the composition, the neuroglial cells just they form nearly more than one half the volume of the total nervous tissue, the supporting and protective tissue. What is ganglia? See, in the brain, at some places, you know that one just the cell bodies collected together. The collection of cell bodies together constitute a mass what is called ganglia. Even in the case of lower group of organisms, we have no brain. We have different types of ganglia. For example, in the case of insects, what I mentioned, just different types of ganglia, the paired ganglia or unpaired ganglia. So the collection of cell bodies together constitute what is called ganglia. What is a nerve fiber? Bundle of what is a nerve? A bundle of nerve fibers together constitute a nerve. Bundle of nerve fibers together constitute a nerve. And just like the muscles, the nerve fibers are also enclosed by membranes, or the nerves, or the bundle of nerve fibers. So a nerve is actually formed by a bundle of nerve fibers. Many bundles of nerve fibers together. Suppose you take a nerve, bundle of nerve fibers and a nerve fiber. This is what is the arrangement. Nerve fiber, bundle of nerve fibers and nerve. And we have three connective tissue membranes responsible for covering the nerves. Now, what do you mean by endometrium? The unit, each nerve fiber is ensheathed or enclosed and enveloped with a thin, delicate, loose connective tissue which is highly vascular. A thin, delicate, loose connective tissue which is highly vascular, and that is called endometrium, a nerve fiber. So a bundle of nerve fibers being enclosed by another connective tissue, what is called perineurium. Epineurium ensheathing a single nerve fiber, and then perineurium just ensheathing a bundle of nerve fibers. We have epineurium, it is now enclosing many bundles of nerve fibers to form a nerve, or we can say the entire nerve is actually ensheathed or enveloped by epineurium, the whole nerve. So the whole nerve is ensheathed or enveloped by epineurium. The bundle of nerve fibers ensheathed by perineurium. Each nerve fiber is ensheathed or enveloped by what is called endoneurium. So that's all about what we have with reference to just the nature and structure of the nerve cells. And after that one we have the conduction of nerve impulses, how far the impulses being conducted, how far the generation of the nerve impulses taking place. And if you are taking the nerve fiber, what do you mean by nerve fiber? The term nerve fiber is applied to mainly an axon, because it is an axon that is responsible for conducting the response impulses, that is from the central nervous system towards the effector organ. That is why when you are saying the nerve fiber, the term implying mainly to the axon, because it is the one which conducts response impulses from, that is what is called the central nervous system to the effector organs. And normally the impulses are conducted because of one phenomenon. So there is always an electrical potential change in a nerve membrane or a nerve fiber. There is always actually an electrical potential change that occurs in a nerve fiber when it conducts electrical impulses. So that's why we can say impulses conducted along the nerve fiber is an electrochemical process. The conduction of impulses along a nerve fiber is an electrochemical process. And you see that when the nerve fibers conduct the impulses at an average velocity or speed of 130 meters per second. When compared to the chemical impulses brought about by the hormones, the impulses conducted by the nervous system is quicker, and it is being conducted at a fast rate of about 130 meters per second. So how far the impulses conducted, and we could see later, and normally this is because of presence of electrical potential difference or called electrical potential change. The electrical potential change that occurs in the nerve fiber is the main cause for the transmission of electrical impulses. That's why we say the conduction of electrical impulses is by means of electrochemical process. And what is the velocity of speed of conduction? It is about 130 meters per second. So we can have, so why we have normally impulses being conducted in the form of electrical impulses? This is because the impulses are being conducted electrically. The main cause for that one is the neurons are highly excitable. So the excitability of neurons are because of their what is called membranes, which are in a polarized state. The polarized state of the membranes or the membranes of the nerve cells are responsible for the conduction of electrical impulses. That is why the neurons are highly excitable. The reason for that one, the membranes of the nerve cells or the neurons are highly polarized or in a polarized state. Now, the membrane of the neuron is in a polarized state. This is because of the presence of some ion channels, namely sodium ion channels, potassium ion channels present on the membrane. So, the polarized state of the nerve cell is because of the presence of many ion channels, mainly the sodium ion channel and potassium ion channel. That is the main reason for the polarization or the polarized state of the membrane. So, you see the protoplasm or the axoplasm enclosed by the nerve fiber axon is called axoplasm, and this axoplasm is normally 10 million times more resistant to electric current than that of a normal copper wire. So, the nerve cells are excitable because they are always in a polarized state. The polarization or the polarity, the membrane of the neuron is polar. The reason for that one, because of the presence of many ion channels, particularly sodium and potassium ion channels, and they are responsible for making electrical potential difference. Now, the axoplasm is highly resistant to electric current. How long? How far? It is about 10 million times more resistant to electric current than a normal copper wire. So, with this I conclude. We will proceed further about the conduction of nerve impulses in the next class.